All right, so far we've looked at the gravitational force on or around the Earth's surface or away from the Earth's surface. Looked at the gravitational force, and now we're going to be able to calculate the acceleration due to gravity at places other than the Earth's surface. Okay, so on the Earth's surface, we know the acceleration due to gravity is what? 9.8 meters per second squared. Okay, and we need to make sure that you understand the difference between the acceleration due to gravity and the gravitational force. Okay, what are the units for the acceleration due to gravity? Meters per second squared, because it's an acceleration. Okay, and what is the variable for the acceleration due to gravity? The variable. When we solve for acceleration due to gravity, what variable is it? G, right? Little g. Okay, so when we solve for the acceleration due to gravity, it's in meters per second squared. When we solve for the gravitational force, what are our units? Newtons. And what is the variable for the gravitational force? Fg. Okay, so there's a difference between those two. So we can now use kind of this gravitational equation, this Newton's universal law of gravitation equation, to end up solving for the acceleration due to gravity at somewhere besides the Earth's surface. So we're going to start with our original equation. So all I'm going to do is walk you through how we get to our new equation, okay? But you don't have to necessarily write down these steps. I'm going to show you how we get there. Okay, so this is our original equation. Gravitational force, right? This looks familiar, hopefully. Yes? Yeah. Okay, good. Okay, so when we're looking at this, we're going to assume that the mass of one of the objects is the mass of the Earth. Okay, that's all we're doing. So we're going to plug in mass of the Earth here instead of m1. That's it. Because we're always going to look at the acceleration due to gravity between an object and the Earth. So the mass of the Earth has to be one of those. We're going to substitute mg in for the force due to gravity, right? And it's the mass of the object times the acceleration due to gravity. Okay, does that make sense so far from here to here? Because another way that we can solve for the gravitational force is taking mass times the acceleration due to gravity. And so far, we've used 9.8 as the acceleration due to gravity, right? So all we're going to do is substitute that in. Then we're going to be able to cancel m2 on either side, which leaves us with this equation. G equals big G times mass of the Earth over r squared. This new equation right here you need in your equation sheet. Uh-huh.
How come when we're finding gravitational things, you didn't use the mass of the Earth?
Right up here?
Yeah, like how come you use the second mass instead of...
Oh, we just picked one of them. It didn't matter if it was M1 or M2. Yeah, just as long as you use the mass of the Earth for one of the objects. It makes no difference whether it's M1 or M2. No. What's the acceleration due to gravity on the top of Mount Everest, which is 8,848 meters above the Earth's surface? This is when we have to be really careful with the wording, right? Is it above the Earth's surface? And if that's the case, what should we do? Add it to the radius of the Earth. Okay, so this is important. Whatever radius goes into our equation needs to be the distance from the center of the Earth to the object, wherever that object is. Okay, so we always want to add in the radius of the Earth if it says it's above the Earth's surface. Okay, if it's on the Earth's surface, then that means our radius is just equal to the radius of the Earth. But if it's anywhere above that, we need to add that distance to the radius of the Earth. Okay? So let's start getting down our variables here. First of all, you need to be able to understand, is it asking you to use this new equation that we learned by solving acceleration due to gravity, or are you trying to find the gravitational force? There's a difference, and it makes a difference on which equation you use. So you need to make sure you pay attention to that and you understand which one is which. Okay? We're solving for acceleration due to gravity, which means we're going to use this equation. Little g equals big G times mass over r squared. Okay, so our radius now we know is the radius of the Earth plus 8,848 meters. Okay, and I wouldn't round that into your calculator because it's going to look just like 6.38 times 10 to the 6. Try to keep that whole number in there. Okay, so it would look like this: 638,848. Right? If you round that back to 6.38 times 10 to the 6, then it doesn't look like our radius changed at all. Okay, there is a little bit of a change. It's not a great magnitude, even though we think Everest is really tall. It's not changing the acceleration due to gravity all that much, but it is changing it a little bit. Okay, so we need to make sure we take that into account. So when we plug it into our equation, what does big G equal to? Good, 6.67 times 10 to the negative 11 times m, which is the mass of the object. Mass of the earth, I'm sorry. Not the mass of the object, mass of the earth. That's backwards. Mass of the earth, my bad. 5.98 times 10 to the 24th over r squared. So we use this radius, 6.388. So here, it does not matter what the mass of this object is at a certain distance from the earth. The only thing that matters is the mass of the earth itself. Go ahead and plug it in. On these problems, we want to try to keep a few decimal places, because if we round, it's not going to look like our acceleration due to gravity changed very much. Okay? Gravity. Keenan, tell me what you got. 9.77 meters per second squared. Good. Do we see a big drastic change between the acceleration due to gravity on the surface of the Earth and at Mount Everest? Not a drastic difference, but there is a little difference. So, do we think we're going to start floating away, when we get to the top of the mountain? Probably not. Okay. Probably still going to think. Things would fall a tiny bit slower, but not enough for us to notice. Okay? By the time you get up there, I don't think you really are going to care what the acceleration due to gravity is. Okay? By the time you finish that walk, I don't think you're really going to care. Okay? If a gravity on a hypothetical planet is 3.21 and the mass is 4.12 times 10 to the 21st, what's the radius of the planet?
So when it says gravity, is that little g or is it F?
What's that tell us?
That's the acceleration.
Yep.
So we're solving for the F.
No. You're solving for the radius.
Yeah.
But it gives us little g, so we're going to set up this equation. G equals mass of the Earth, or really mass of the planet, right? We just use Earth because most of the time we're looking at Earth. So we can use any planet right there. Okay, except this time they gave us the acceleration due to gravity, so that's little g. You can do that, but you need to move this over first. Move g over first, and then you can switch them places. So algebraically, my first step here is going to be moving g to the other side. And then I would switch those two places. Things that orbit the Earth. Okay, there's a different equation that we use for satellites. So this one you might want to write satellites on your equation sheet because we have a couple that just are specific with satellites. Okay. This is the same equation as centripetal acceleration, right? This is not a new equation, but we are going to add some new ones on there. Okay, so this is the acceleration at which that object is going to move. It doesn't make any difference basically on its gravitational force when we get into that aspect. But this is just its velocity divided by the radius, or how far it is from the Earth's core, would equal the acceleration there. To find the force holding it in its place, we're going to use Newton's second law. And then we are going to plug that into our equation, right? This doesn't look any... All we're doing is plugging in the mass of the satellite instead of the mass of the object. Okay, so that's not a change. Okay? Since the force of gravity is what's holding these in place, we're going to combine a couple of equations, okay? This is centripetal force, but it's not really centripetal force that's holding it in place. This time it is the gravitational force from the Earth that's holding it in its circular orbit. So we're going to do a little substitution here. Okay? Right? This is the FG equation. FG equals big G m1 m2 over r squared. This is centripetal force. So we can combine these two equations, and our last step is we're going to cancel out the mass of the satellite on both sides, which leaves us with this equation.
Wait, so should I have written down?
You don't have to write down this one, no. I'm just working you through until this part.
Okay. Oh.
These are our two that we probably need to have done.
So not the FR one?
No, you don't. You already have these ones.
Okay.
No. Sorry. Okay, these last two are what we should probably have down. G equals mass of the Earth over r squared equals v2 or v squared over r, or this is even more of an expansion, right? We're taking velocity 2 pi r squared over t squared. Okay, either one of those. Those are two different sets. This is one equation, right? And they're set equal to each other. This second equation is only different in the fact that we substituted for v squared. We put in 2 pi r over t, and we squared that for velocity. That's the only difference, right? Because 2 pi r over t is the equation for velocity. So basically, the only difference in these equations is if we're given velocity, we're probably going to use this equation. If we're not given velocity, we're probably going to use this one, okay? Or you could just solve for velocity and plug it in here. It makes no difference, okay? No, nothing that should throw you off there, hopefully. Okay? But this equation right here is specific for satellite, so you might want to write that one satellite by that. Okay, it's specific for satellites. Okay, are we ready to try some?
Sure.
Yeah, sure. All right, determine the height above the Earth's surface a satellite must orbit in order to stay on the same point of the equator during its entire orbit, which is called a geosynchronous satellite. Okay? Like I know what that means. Okay? Obviously, to stay on the same point at the equator. All that means is that it's not shifting, it's not moving on the axis, it's staying at that exact same point around the equator the whole time. Okay? So it's not being pulled one way or the other. Staying at the same. Our goal is to find R. Okay, in order for us to understand why it is moving at the same speed as the Earth, it's because that's what that word means, that geosynchronous satellite. It's staying at the same point on the equator. Okay, so let's say it's got a longitude and latitude point that it's right above on the Earth. Does that make sense? Like if you point a little laser beam right down the Earth, okay? As the Earth rotates and as the satellite rotates, it's staying at that same point the whole time. So it's going to rotate at the same point. The satellite's probably having to move at a greater speed because its radius is larger. Okay, so let's look at a picture of what's happening here. Okay, here's the Earth. Here is the satellite. Here's the Earth. Here's our little satellite. So as it orbits, let's say it's going to keep this. It's going to be at that spot around the Earth all the time. So as the Earth moves this direction, right, and the satellite moves, it would keep moving and going at the same, basically that same spot. It has the same period. It does not mean it has the same speed, right? This is having to cover a lot more distance in the same amount of time than the Earth does. Does that make sense? Okay, so same period but not the same speed. So let's calculate the velocity by basically knowing what the period of the Earth is. Okay, how long does it take the Earth to spin around one time? No, not orbit the sun. To spin. 24 hours. Okay. So T is equal to 24 hours. Is that what we want our units to be in?
No.
We want it to be in what? Seconds. Good.
No.
Okay, so times, times 3,600 seconds, right? In 1 hour.
Cute. Oh. Wait, is it times 3600?
Yeah, you should have a lot bigger number of seconds than you do of hours.
86,400.
Okay, and we're not given the velocity here, but we know that the period. So we're probably going to use this equation, right? We could solve for velocity and then plug it in, or we could just use this equation since we know the period, we know the radius of the Earth, we know the mass of the Earth, we know the radius again. Okay. I'm sorry, we're not using the radius of the Earth. My bad. My bad. We are solving for r. I said that wrong. We're trying to find the height above the Earth's surface. So we want to find, and here's Earth again, okay? We want to find the distance. If here's our satellite, the radius that we solve for will be from the center of the Earth to the object. So we can't just use the radius of the Earth because we want the whole distance. We're solving for r. Yes, I'm sorry, I said that wrong the first time. Okay, this problem is going to require a lot of algebra, so you needed to stay with me here. Okay, look how many r's there are. R squared, r squared again. Okay, so they're going to cancel. We're going to have to do some algebra, so just please stay with me. Ask questions if you're not understanding where these are coming from. I am going to put on a blank screen here so I have a little bit more room to write. Is everyone good with that? Okay, we're good? Okay. Let's start with our equation. I'm just going to put that up here by itself. Okay, G times mass of the Earth over r squared equals 2 pi r, that whole term squared over r times t squared. Do we understand why t only is squared down here?
Yeah, because it's just b squared.
Yeah, it's part of that velocity, which has to be squared. Okay, so that means top and bottom. All right, let's start looking at some numbers here. I start plugging in. So 6.67 times 10 to the negative 11th, 5.98 times 10 to the 24th. If you are ready to do this on your own or want to try it on your own, that's fine, but I'm going to walk through this for everyone else. Okay. Algebraically, our next step, I'm going to go ahead and square this whole term right here. Okay, so I'm just going to replace that, and it would be 4 times pi squared times r squared. Okay? Okay, our first step right off the bat, can't we cancel this r? We can cancel one of them, right? Get rid of one of them, because r squared is r times r, and we've got an r on the bottom. We good with that? Okay, next step, we can go lots of different ways here. Okay, it does not really matter what way we want to go.
Wait, did you distribute the square on the outside?
I did distribute the square on the outside of this one, yeah. Right? 2 pi r squared would give us 4 times pi squared times r squared. Okay, so I just replaced that. Okay, algebraically, there's lots of ways that we could go here. Anyone have a preference? I kind of want to get rid of fractions.
Yeah, sure.
Okay, I don't like fractions. So I'm going to multiply by this on both sides. Okay. So I'm going to take that times g. Okay, so these two combined, 86,400 squared times this, gives us 0.498 times 5.98 times 10 to the 24th over r squared equals 4 pi squared r squared. Okay, because this is done over here. We don't have an R on the bottom anymore.
Wait, isn't it just R?
You're right, it's just R. Sorry. Okay, what can we do next? I'm telling you, there's lots of ways we can do this. We could get R squared to the other side. Okay, so times R squared times R squared. So now our R's are done. And we can multiply these two together as well. Again, there's lots of different ways you can do this. This is not the only path you can take to get there. What's R times R squared? R cubed. Step, we're going to divide by 4, divide by pi squared. Okay, so divide by 4 and pi squared. Be careful here when you do this in your calculator in the denominator. So I would hit divide by 4 equals, then divided by parentheses pi squared. Okay, that's what I would probably do, just to make sure. And I got about 7.54 times 10 to the 22nd equals R cubed. And do we know how to cubed root in our calculator?
Math, cube root.
Yeah, you could do math and then 3, second answer. Oops, no, it does it for you. Math. Oh.
No, I did it wrong. Oh, I forgot the. Oh, wait.
It's math 4, not math 3.
Oh, no, that's not exactly. Does this make sense? I got 7. Bless you.
Okay, so the radius that we got by taking the cubed root is 4.224647 meters. Is that our final answer? Close enough. Is it our final answer? Why not? We want to know above the surface of the earth, so we need to subtract out the radius of the earth. Final answer up here, I got about 3.59 times 10 to the 7th meters. What speed would that satellite be orbiting? What speed would our satellite be orbiting? So we know that the period of that is the same as the Earth. So the period doesn't change. The R that we plug in here, what R value is that going to be? The one from the surface of the Earth or from the center of the Earth? From the center. We always want it from the center of the Earth. So you need to take the number before you subtract out the radius of the Earth.